Welcome back into Calculus 3. Today we will talk about the cross product. Prior to doing that though, what we want to talk about, we need to introduce the concept of what it means to be orthogonal. Right now, simply what orthogonal means is if I give you two vectors, let's call them u and v. Let's put that underneath, u and v. And I take their dot product here will be 0. Right, so two vectors, I take the dot product, I get 0. That is the definition of what it means to be orthogonal. But let's think about what this means geometrically. Right, and I should have a visual come up over here. But if I take this geometrically, think about the angle between these two vectors. And I have cosine of theta is equal to u dot v all over the magnitude of uv. And you can put the lines underneath. Right, well, if they equal 0 for their dot product, that implies cosine of theta is equal to 0. And now if we take the inverse, right, cosine inverse of 0, right, this implies theta is equal to pi over 2. Right, well, what is pi over 2? Pi over 2 is a right angle, right? So if we're looking at these, right, two vectors, and they have a dot product equal to 0, that implies geometrically, right, they are forming a right angle between them, right, or they're perpendicular to each other. So that is what it means for two vectors to be orthogonal, right? Okay, so now we're going to take this idea of orthogonal, build upon it for cross product. All right, so let's go over here. We'll say the cross product right? The whole idea for a cross product is it's a binary operation, meaning if I give you two vectors, it's going to give me a vector coming out. So two vectors go in, one vector comes out, right? So let's say I give you two vectors, right? We'll say u and v, and I know I keep using, pretend these are bold, right? That'll work as well, right? U and v, right? I'm going to input these in, and I'll get another vector coming out. We'll call it w. Right, and what's so special about w is that w will be orthogonal to both to u and v. It'll be orthogonal to both. Right, so if you give me two vectors, u and v, they don't have to be orthogonal. It can be random vectors, right? And I input them in, right, and we'll talk about how we actually compute the cross product here in the next part of the video. I'll get another vector coming out that is orthogonal to both, right? So that's what we're going to talk about. Now, what does it mean for it to be orthogonal to both? Just so we remember our definition here, that implies that u dot w will be equal to 0, and it also implies that v dot w will be equal to 0. Right, both of these statements will be true. Now there's a proof that goes along with this. I won't make us walk through the proof. Maybe I'll include a link in case you are interested. But this is it for the introduction. Now we'll actually get into the computation of how do we find this vector w that is orthogonal to both the other two. Right, so I will see you in the next part of the video. So before we get into the computation of the cross product, we need to be familiar with two formulas, right? The determinant of a 3x3 and 2x2, and you'll find those both over here, right? So feel free, pause the videos, write those down because we're going to need them. Okay, so let's go ahead and pick two arbitrary vectors. We'll say A and B, right? So A1, A2, and A3. And something to note as I'm writing this is notice that these are three-dimensional vectors. For the cross product, we are limited to the third dimension. Okay? So again, we're utilizing these two equations over here. And now I'm going to I'm going to take my two vectors as well as the unit vector and write it over here, right? So let's go ahead. I'll write out. We have the determinant of some matrix that we're going to form here with our unit vectors, I, j, and k. And we're going to take our pieces here, A1, A2, A3, and B1, B2, and B3. All right? So our first step is we want to apply the 3x3 formula, right? The 3x3 formula. Okay, so what's happening here? Let's just start off with our very first component is going to be I, right? So we're using I, and now we're going to block out the first column and use the determinant of this 2x2, which we'll get to in a second. But essentially what happens is, right, we block out the first column in the first row, and look what we're left over with. We're left with A2, A3, B2, B3, I, and we'll keep going, right? So now we're moving on to J. Now the formula states that we have to switch signs here. And again, if you're wondering where is this coming from, the determinant, it's a topic that you'll talk about more in linear algebra. So we'll say minus. Now we're blocking out the second column, and we're left with A1, A3, B1, B3, and it's going to be J. And we're doing it one more time, blocking out the third column of K, right? So block out the third column, we'll have a plus sign here, and we're going to be left with A1, A2. Let's write this down. A1, A2, B1, B2. Okay, right, so now we have applied the 3x3 formula. Okay, so that's our first step. The next step, right, is now applying the 2x2 formula. So what's happening with the 2x2s? We're multiplying the diagonal, right, so A2 times B3, and we're subtracting the other diagonal, right? So what we end up with is A2 times B3 minus A3 times B2. I, and this is in physics notation, so eventually you can see we're going to just switch over to vector notation, or whatever notation it's called by name. We have minus A1 times B3 minus A3 times B1, and this is J. And last one, right, we have A1 times B2 minus A2 times B1, K. All right. Okay, so now what do we have? We have physics notation, computationally, not very helpful for us math people, so let's go ahead and put this into a vector, right? We're just stealing the coefficients here, right? So this first piece is A2, B3 minus A3, B2. Now it's up to you whether you want to distribute this negative sign to each piece. I'm just going to leave it on the outside for right now. A1, B3 minus A3, B1, comma, last part, A1, B2 minus A2, B1, bracket. Right, okay. So here's our formula, right? Write it out. Now again, I know it seems like a lengthy explanation, but essentially all we're gonna do here is we just start blocking out columns. And the better we get with 2x2 determinants, right? So eventually we want to get to doing these things in our head, right? We can multiply across, subtract the other one, right? So eventually if we can block it out, we can compute the determinant, right? This is actually a fairly fast process, the better we are with 2x2 determinants, right? So this is our equation. We'll go through an actual example with some actual numbers here moving forward, but again, write these equations down. You will need them, right? Again, this is coming from a topic in linear algebra, but for right now, we're just going to take the formula as is. All right, I will see you in the example following. Let's jump into an example now, actually using some numbers with the cross product. So I'm going to give us two vectors here. Let's go ahead and write these down. We have A. We're going to say A is going to be equal to, let's do 2, 4, and -3. and we will say B will be equal to, let's go ahead, I'll use my numbers here, 1, negative 2, and 2. Awesome. Now again, I have over here the equations for a 3 by 3 and a 2 by 2 because we need both, right? So first things first, let's go ahead and set up our determinant. So we'll put some lines here. We'll put our I, J, and K. And let's go ahead and fill it in, right? We have A, 2, 4, negative 3, 1, negative 2, and 2. Awesome. Okay, so first things first, let's go ahead and do our 3 by 3. Now I'm going to break it up into pieces. So I'm going to do I, J, K all separately, right? So let's start with I. We have our 2 by 2 in which we're blocking out the first column. So we have 4, negative 3, negative 2, and 2. And this is for I. Let's go ahead and write out the next one. So we have a negative J, right? So negative J, I'm blocking out the second column. I have 2, 2, or 2, negative 3. Let's go this way. 2, negative 3. And I have 1, 2. And this is J. And then I have K, so I'm blocking out the third column. We'll put a plus sign just so we know. Right, and we'll go ahead, we'll block out third column, so we have 2, 4, and 1, negative 2. Okay. All right, so let's go ahead. Again, the faster we are with solving 2 by 2 determinants, the easier this will become. So what do we have? 4 times 2, right? Looking at the diagonal, this is 4 times 2, 8, minus a positive 6, right? So minus a positive 6, there we go. And I'll just put I here, and we'll simplify it over here. Now we'll do J. What do we have? So this is a negative, let's not forget. We have 2 times 2, 4, minus negative 3 times 1, so plus 3, J. And lastly, we have K here, negative 4, minus 4, K. Awesome. Okay, so now let's go ahead and we're going to simplify. Let's just write it out right below. What do we have? We have 8 minus 6, 2i. What's next? Negative 7j. And finally, minus 8k. And again, I'm not one for really physics notation, so we will have 2, negative 7, negative 8. Awesome, right? So now we have, what are we solving for again? The cross product is going to give us another vector, right? This vector is going to be orthogonal to both A and B, right? Well, let's double check. Right, I'm going to do the first one with this, but let's label this one C, just so it has some name here. Right, this is the vector that is orthogonal to A and B, and let's check to see if C is orthogonal to A. Right, so what does that mean to be orthogonal? Well, that means that the dot product of A dot C should be equal to 0. Right, and I'm going to do this just so I don't waste any space. So what do I have? A, which is 2, times 2, so I have 4, plus 4 times negative 7, negative 28, plus negative 3 times negative 8, so plus 24. And what do we get here? Negative 24 plus 24, we get a 0. So we have confirmed that C is indeed orthogonal to A. Now you should go double check as an exercise. Is C orthogonal to B, right? It should be the way we constructed it. So it's a way that we can double check our math, right? So I'll leave this example. Again, I have the determinant rules as well as a visual over here. If you have any questions on this example, let me know, but I will see you in the next example. All right, welcome back. Let's go ahead. We're going to do another application/example. But first I need to introduce a theorem here. And so we're going to say, let's do the magnitude of A cross B, right? So the cross product of A and B, but we'll take its magnitude, is going to be equal to the magnitude of A times the magnitude of B, sine of theta. Right, so I have a visual over here, right? This is given to us. Maybe I'll include a link to a proof of this. But what is being broken down here? Now remember, through vector addition, two vectors A and B will form a parallelogram, right? So what do we have here by our visual? Well, A, right, forms the width of our parallelogram, where B, sine of theta, forms the height. And so what do we have? If we're multiplying these two things together, we have the width times the height of a parallelogram. That gives us the area, right? And by equality, since these two are equal to each other, right, either side of this will give me the area of our parallelogram. Okay, so let's do the easier of the two examples. Let's say example 1, right, and it's all based off of what information we have. Let's say I give you the magnitudes. Let's say magnitude of A is equal to 12. Magnitude of B is equal to 5. And let's say theta is equal to, let's do pi over 3. All right, so in this case, right, I have my entire right-hand side. So if I want to find the area of a parallelogram, easy as multiplying and making sure I know my trig circle, right? So we have this is equal to 12 times 5, sine of pi over 3. Anybody? Sine of pi over 3, first quadrant. We're going to get, that is correct, rad 3 over 2. So our answer ends up being 30 rad 3. Awesome. Okay. So, right, easier of the two examples. What if I want to calculate the area of a parallelogram, but I just give you two vectors? What does that mean? So let's say A is equal to, we'll just do the easy 1, 2, 3. And let's say B we'll do equal to 2, 1, negative 1. All right, now we can form our determinant, right, for our cross product with ijk. So let's go ahead and do that. I'm going to write it here. We'll go down a little bit more. ijk. And again, the better we are with 2 by 2 determinants, the easier this will be. So 1, 2, 3. 2, 1, negative 1. Right, so if I want to just find the first component of this vector, I block out my first column I, and I'm left with, what do I have? 2 and 3, 1, negative 1. I minus, now I block out j, 1, 3, 2, negative 1, and now I block out k, 1, 2, 2, 1. Okay. Awesome. So, again, I'm going to do these 2 by 2s in my head. What do we get? 2 times negative 1, negative 2, minus 3, we're going to get negative 5. Right, I'm just going to write this straight into vector notation. All right, so negative 5. What's next? 1 times negative 1 minus 6, right? Negative 1 minus 6, negative 7, but we also have a plus sign, so plus 7. Let's make sure I did that right. 1 times negative 1 minus 6, negative 7. Perfect. Becomes positive, comma, and then we have 1 times 1, 1 minus 4, negative 3. Awesome. So now we have our vector, and maybe we should double check really quick. What do we have? We have -5 plus 14, -9, right? So that works. I'm just computing the dot product really quick between this vector here and A, right? 1 times -5, -5, 2 times 14, or 2 times 7, 14. We're left with a +9, and we get rid of that +9 with that -9. You should verify that though. Make sure that this vector is indeed orthogonal to both A and B. Right? Now, once we have that, we need to go back and remember how we solve for a magnitude. Right? So in this case, right, if I want the magnitude of this vector, all I'm going to do is the square root of -5 squared, 25, plus 7 squared, 49, plus 3 squared, 9. And let's see, what do I end up with? 34 plus 50, 84, 83. This is the square root of 83, right? Would be our area of our parallelogram, right? Remember what we're solving for. We're solving for area. And I don't believe 83 can be broken down. I think it is a prime number. So we will leave it as is, right? So again, double check though, right? We checked A. Let's go ahead and check B. -5 times 2, -10, plus 7, plus 3. We're good to go. Awesome, right? So you have some visuals over here. We did 2 dimensions, right? So this is the area of a 2-dimensional figure. In our next example, we'll talk about if we have 3 dimensions, right? So in this case, it's a parallelogram. In 3 dimensions, it's what's called a parallelepiped. I think I pronounced that right. I will see you in the next example. All right, and last example here, we're going to jump into, right, how do we find the volume of a parallelepiped? Now, very similar, right, we're going to need the cross product again, but instead our equation will read as the volume is equal to the determinant. Now, I know we use this as magnitude, but the determinant of A dot B cross C, and all of these are vectors, of course. Right? Now, the determinant, same way we've been doing the determinant. Normally we were using I, J, and K. The only difference now is we're going to use A instead of I, J, K. So let's just get into an example and we'll see it as it goes. Again, I should have a visual over here. Let's give you 3 different vectors. So let's go with A, and we'll just make these up as we go. 2, 1, -1. Let's say B is equal to, I don't know, 3, 5, 4. And C, we'll do an easy one here. We'll do 1, 1, -1. Awesome. Okay. So let's go ahead and compute. So first thing we want to do is set up our matrix, right? So let's go ahead. Or I mean our determinant and our matrix at the same time. We'll use this one. This one seems to be running out. So we have our determinant, and we're going to put A at the top. So 2, 1, -1. We have 3, 5, 4, and 1, 1, -1. Now I'm going to break this down into the 2x2 cases, right? Just so we can see it now that we're not using I, J, and K. But again, we want to get better at performing determinants, especially in 2x2s, so that way we don't have to write down as many steps. So our first case, right, normally we'd write I, but we're going to use 2 here. So 2, and now we have, we'll write the determinant still. We won't skip that step. We are blocking out column 1, so 5, 4. And again, as you get better at these, you can skip ahead in the video. 1, -1, minus, now we're on to 1, and now blocking out column 2, 3, 4, 1, -1, and we have a -1, and lastly blocking out column 3, we'll have 3, 5, 1, 1. And we squeezed it in there. 1, 1. Perfect. Okay, so now computing some 2 by 2 determinants. We have, let's go ahead, 2, and I'm going to do this part in my head. 5 times negative 1, negative 5, minus 4, negative 9. Moving on, we have minus, this is going to be 3 times negative 1, negative 3, minus 4, so negative 7, but we have another negative sign, so we'll just put plus 7. We don't need to multiply that by 1, we know how to do that. And now we have minus 3 times 1, 3, minus 5, negative 2, times a negative 1, plus 2. So after everything is said and done, this ends up being negative 18 plus 9 gives us a negative 9 volume. Now you might wonder, what is a negative 9 volume? So it depends on what quadrant, and in 3 dimensions we have 8 quadrants, so it depends on what quadrant it's hanging out in, but that volume would be 9, and then its orientation is in a negative space, right? So negative 9 volume. So what have we gone through? We've gone through solving a cross product, right? What is a cross product? Well, it's a vector that is orthogonal to both the other 2 vectors. We used that knowledge to go ahead and find the area of a parallelogram, and then we took it up 1 dimension and found the volume of a parallelepiped. Right, so that is it for this video. Hope you guys enjoyed. I will see you in the next one. Thanks, everyone.